Good morning, everyone. How are you? Come on in, everyone. Come on in. I know you, like Miss Chris, you're early today. I decided to be early today. I was able to secure time off from my other job, which allows me to be here with you guys this morning. So come on in, come on in, come on in, come on in, come on in. If you can hear me, please click like, hit a heart, thumbs up, all that good stuff. Let me know that you can hear me. Thank you. Well, guys, we are going to get started and continue with our geometry lesson. As you can see, tomorrow we are off. I know, right? So, since I am up early, I want to go ahead and conclude our geometry lesson. Just going through the basics, what you will see in geometry, what are the key components for geometry, and wanting you guys to understand what does entail when you take geometry. So, since I know you can hear me, we're going to go ahead and get started, okay? All right, first up on the agenda, we have the informal geometry and measurements, all that good stuff, right? So, of course, you know, in the corner, we have something that is waiting on you, beautiful people. But we will get to that in a minute. First thing we are going to talk about is a point. And excuse my point for not being round, but a point nonetheless. So, a point typically is represented by a dot. It also has location but no size, and it has no dimension. Typically, when you see a point, it's usually a represent of where, like point A to point B, point C to point D. But before you can have a point to a point, you must start with an actual point. And usually points are on a coordinate plane. And so when we're looking at points, we usually look at them in the form of where is it between X and Y. So my X and Y could be 1 comma 4, 2 comma -3, -3 comma -5, or 4 comma -2, all of which are on the Cartesian plane, which is what we learned about, I want to say about last week, revisited last week. And so our points allows us to start our location. It is the beginning of all of our geometry movements. And so the point helps guide us of where we are, and then it gives us a direction of where we're heading from the beginning. So anytime you're seeing a point, more than likely you are dealing with a point A or point C or a point zero, a point triple Z, depending on what the point is labeled as. And typically, when you're looking for that point, you're looking for the location of the point, and the location of the point is typically on a Cartesian plane or a graph. And so know that when you're dealing with the point, all you're going to be giving when asking about the point is the X and the Y value of the location of that point. All right. Next, we have a line segment. Now, a line segment, remember how I was talking about the point A to point B? Well, a line segment is exactly what you're describing when you say you're going from point A to point B. So, A to B. So, a line segment has a start point and an end point, or two endpoints. And when you're dealing with a line segment, know that you have two different points. Those points are stopping points. It is not continuous. It will stay where it is. And typically you'll see line segments for measurement. So you'll measure it either in centimeters or inches, depending on what the question is requesting, or is asking you from point A to point B, how long is the distance, which is the measurement of time. So whenever you see two dots with a line in between, or two endpoints with a line in between, know that that is a line segment, because that piece of line has a beginning point, end point, to a start point, stop point. So as long as you remember that, you'll always know what a line segment is. Then that shifts from a line segment to array. Now, the difference between a line segment and array, well, do it this way. A line segment, of course, has two start and end points. Well, array is a start point going into one direction. And either the direction is to the left, to the right, going up, going down. So whenever you're dealing with array, R-A-Y, know that you have a start point and you're going in one direction. So you'll always have one arrow. That is the difference between a line segment and array. Line segment, you start, you end. Array, you start and you continue in one direction. Next up, we have an actual line. Now, when you hear and talk about lines, lines are from left to right or up and down. But lines are biconditional. Remember when we talked about biconditionals? They are continuous in two directions. So either the line is going to go left to right forever, or the line is going to go up and down forever, which is how we see and understand our perpendicular lines as well as our Cartesian plane, which allows us to say that my X and my Y my X goes from left to right and my Y goes up and down. So remember, lines are continuous and they go in two directions forever. They do not stop. They go from negative infinity to infinity. And of course, infinity has no true measurement, but it is considered a number. So anytime you are dealing with lines, know that those lines are going in two directions at one time. So line segment, two stopping points. Array, a start point and going into one direction forever. Lines, two directions at the same time forever, continuously, never ending. So when you're dealing with these type of lines, you will see points on these lines. And typically, if you see 3 or more points like A, X, and B, those are considered collinear. Collinear simply means these points are on the same line. Collinear means these points are on the same line. They are all on the same line. So if it's on the same line, then it's collinear. Now, say for instance, I have point A over here, point B over here, and then point X over here. Well, those are considered non-collinear. And the reason why they're non-collinear is they don't form a line. In order for you to be collinear, you must form a line, and it must be on the same line. So if I drew a line between A and X, and then drew a line between B, well, we have proven that, hey, they may be parallel lines, but they're not collinear. So whenever you want a collinear line, or to determine whether it's collinear or not, you can draw a line through the points. And if you are able to connect all points on that line, that's what makes it collinear. But if you can only get some of the points, or not really, if you can only get some of the points, one of the point when you're drawing your line, that means they're no longer collinear. They're non-collinear. Now, you also have parallel lines like these, which means they go on forever, never touching. And if you remember, the reason why they don't touch from last week is because they have the same slope. So if you have the same slope between lines, they will never touch. They will never cross. They will never meet. They'll be forever going in negative infinity to infinity, never touching. And then, of course, I mentioned earlier about perpendicular lines, which perpendicular lines is an intersection. An intersection is where two lines meet. An intersection is where two lines meet. Parallel, they never meet. Intersection, they do meet. Now, what's special about a perpendicular line and perpendicular lines as a whole, perpendicular lines, not only do they intersect, but they intersect making perfect right angles. So anytime you're dealing with perpendicular lines, know that they intersect making perfect right angles on all sides of its intersection. Any questions on lines, points, line segments, rays, perpendicular, parallel? Any questions on that? Collinear, any questions on that? All right. Okay, guys. Remember I said I have a couple of pictures that I wanted you to see? Well, there are some things that we deal with called angles. Angles are where two rays meet, or two rays that have the same starting point and they're going into two different directions. So anytime you are dealing with an angle, know that it is two rays that have the same starting point and they're going into two different directions. Now, typically you'll see three types of angles. Move this to the side for a bit. You will see acute angles, right angles, and obtuse angles. Now, acute angles, right angles, obtuse angles. What are they and what do they mean? Acute simply means less than 90 degrees. So 89 or less is considered an acute angle. Typically, it looks like a small sideways V, and it is always measured with an arc, like here. So if my angle measurement of degree is 75, and I ask you to identify that angle, you would say, hey, this is an acute angle. Now, a right angle. Most of you have seen a right angle. Most of you know what a right angle is. For those who do not, a right angle is exactly 90 degrees. It looks like the letter L, and it has this little box that is shaped inside of it to denote that it is 90 degrees. So to determine if an angle is 90 degrees, it will one have a box, and typically the box is red. You will see a red box inside of the angle. So angle right will always be 90 degrees because it's exactly 90 degrees because it's straight up and straight out. if that makes sense. So it goes straight up forever and it goes straight out forever with the two rays that have a start point and makes the letter L, has a red box inside of it. If it has those two elements, most importantly, if it has the red box, sometimes you'll even get a black box. But as long as it has a box out of it, know that you are dealing with a right angle. Not a left angle, a right angle. So, right angles, exactly 90 degrees. Acute angles, 89 or less than 90 degrees. Obtuse angle. Obtuse angle, of course, you guessed it, is greater than 90 degrees, but is less than 180 degrees. Now, an obtuse angle, of course, is an outstretched, I would say an outstretched V. And it also has an arc like the one we drew in the middle of it. And it's always greater than 90, but it's less than 180. And of course, the greatest one of them all is considered a straight line. A straight line, as you would imagine, is a straight line or straight angle. Straight angle is a measurement of 180 degrees. It has a perfect circular arch and it goes in two directions forever and a day. So, whenever you are measuring and it says, hey, this angle is exactly 180 degrees, well, this angle that's exactly 180 degrees is you can either call it a straight angle or a straight line. But know that it's 180. So, first angle is acute, 89 or less. Second angle is a right, exactly 90. Third angle is an obtuse, 90 to 179. And a straight angle or straight line, exactly 180 degrees. Now, when you are dealing with these angles and you want to find their measurements, what you want is a protractor. Now, protractors allows you to measure your angle. It tells you exactly how much your angle degree is. So you'll either see it as an angle going clockwise, an angle going counterclockwise, or you may see one that has both of them together, which means it can go in both directions when you're trying to measure your angle. So as you can see, in both of these, my 90 degree is straight up. And straight out. See that? 90-degree angle is straight up, straight out. That's what makes it a right angle. Also, you see these little tick marks in the middle? Those are the actual each degree angle tick mark. So and then the middle tick will, of course, would be 5. Those are the ones that denote as 5. So the ones in the middle for here would be 5. That one would be 15, 25, 35, and so on. And so you will get your measurement by simply holding your protractor, especially if you're looking for a specific measurement of an angle. So say for instance, you want to you have an angle, and it's typically you make sure that one of the sides is straight down, so that way you can measure it. Some may be up in the air, but even if they're up in the air, you can take your protractor and line it against the one that's up in the air, and it allows you to still measure your angles. So you'll have a line here and maybe a line going here. So if you are measuring your angle, you notice that, hey, my angle measurement of degree, it is 40 degrees. Why? Because when I measure this angle, the stop point and end point, the start point is at 0 and my end point is at 40. So if my line stops on a specific line, that makes that the degree angle. And you can always use this to get the exact measurement of your degree angle. Any questions? All right, moving on. All right, so you are going to now learn about triangles. And you're going to see these a lot in geometry. A lot of geometry is based off of triangular measure, especially the right triangle. Because typically when you're dealing with the degree measurement, or if you're trying to find out the distance with certain points, typically is based off of a right triangle. So now, I'm going to show you guys 3 types of triangles. You have, well, two types of triangles based on sides. Well, 3 types of triangles, and they're either based on their size or based on their angles. So first ones will be of the sides. So typically you have an isosceles triangle. Isosceles triangle simply means 2 of my sides equal each other. Scalene means none of my sides are equal. They all are different sides. And of course, equilateral, that means all of my sides equal each other. So if all of my sides equal each other, that means all of my angles equal each other. And typically a equilateral is an acute triangle. An equilateral triangle is typically or is an acute triangle. So if all my sides are equal, that means all of my angles are equal. Now, the measurement inside of a triangle is 180 degrees. So now if I have an equilateral triangle and all of my angles, all of my sides to each other, that means all of my angles equal each other. So if all of my angles equal each other, they're acute. And how do we know? Because if I take 180 and I divide it by 3, that equals 60. So an equilateral triangle measurement of each angle inside will always be 60 degrees because 60 plus 60 plus 60, that's 180. Therefore, an equilateral triangle, meaning all of my sides equal, is also an acute triangle because all of my angles equal, and all of my angles equal 60 degrees. Now, typically, just a typical thing, you'll have the equilateral, the scalene, and the isosceles to determine if triangles are congruent to each other based on their size or based on their angles, which we will touch base on in a little bit. But of course, I mentioned that we have sides that are equal. We also have angles of our triangles that we measure. So therefore, you may have an equilateral, which of course that means you have an acute triangle, which means either one or all of your angles are acute. Then you have a right triangle. Right triangle is where a lot of our measurements of geometry comes from. The Pythagorean theorem, sine, cosine, and tangent, which is our trigonometry measurements, which we will see some of next week, as well as some of the final week of our month tutoring. But right triangle simply means my triangle has exactly one 90-degree angle. And of course, it's usually denoted by a black or a red box. But if it's a right triangle, it's going to be denoted with a box regardless. It means it has exactly one 90-degree angle inside of it. So now we also have an obtuse triangle, and of course the obtuse triangle simply means you have one angle that is more try that again. There we go. So obtuse simply means one of my angles is greater than 90 degrees. Now, can you have a straight line inside of a triangle? No, you cannot. Simply put, a triangle is a straight line with that is bent into three sides. So if you take it apart, it is a straight line. So you can't have a 180-degree angle inside of a triangle because the triangle itself is the measurement of 180 degrees. So the only options you have are acute, right, and obtuse based on your angles. Any questions? Moving right along, we are introduced to a postulate. What you will see are postulates, theorems, and proofs. And the way you can prove a proof is through postulates and theorem. So the first postulate that you come across postulate 1 says through two distinctive points, there's exactly one line. So you remember when I was talking about point A to point B? Well, if you draw a line through it, it's exactly one line that can go through it with these two distinctive points. So postulate 1 says through two distinctive points, there's exactly one line. So if these points are on the same side, meaning they're on the same line, the way you can tell is when you draw your line extended out. So from point A to point B, that is considered a line. Also, if you do point A here and point B here, it still means they have exactly one line. So no matter how you draw your points, know that they can be connected based on location. Now, there will be some where you can't connect them all. And of course, if you can't connect them all, they're what? Non-collinear. So know that two distinctive points is definitely collinear, and it gives you exactly one line. All right. Postulate number 2. Postulate number 2 says the measurement of any line segment is a unique positive number. So that means when you're measuring your line segments from point A to point B, they can never be negative. Also, postulate 2 is called the ruler postulate. Simply mean you are measuring point A to point B. So when you're dealing with point A to point B measurement, that is called the ruler postulate or postulate 2. Now, if you're going from point A to point B, we typically call this the distance. The distance is always between 2 points, and it is the length of the line segment that joins the 2 points. So the ruler postulate comes in handy because guess what? We are measuring what? The distance from point A to point B. What is the distance? Now, to find, actually, let's see. This way. Postulate 3, which is also segment addition postulate. Sometimes you'll have a point you'll have a point. It may not be exactly in the middle, but it's in the middle of point A point B. Typically, when you have a point like that, what it does, it gives you how you can do the measurement or how you can find the total measurement of your segment. So say for instance, from A to X is 7 and from X to B is 5. That means A and B together is 12. So postulate 3 is the segment addition, which means if X is a point of A and B, then AX plus XB equals AB. So 7 plus 5, that gives me my total segment measure, which is 12. So with this postulate, this lets you know how to add your segment if you have 3 points. Any questions on postulate 3? Now, you will see a lot of things going on with line segments and lines. 2 things that stand out the most with line segment and lines are congruency and the midpoint. Now, congruency or congruent line or line segment are 2 lines that have the same length. Simply put, they're equal to each other. So congruency or being congruent means they are similar and they are equal. They are of same length. And so when you're looking for congruency, you have a congruent line, you have a congruent line segment, you have congruent triangles. And to determine if they are congruent, typically they are similar looking to each other. And they might also have the same type of markings. So if I have two triangles and they have the similar markings in the same spot, like so, then those are considered congruent triangles. Same thing for line segments. If the measurement of line segment AB is 20, then I should know that the measurement of CD will also be 20. So congruency tell me they are of same length and they will always be equal to each other. And typically that comes in handy when you're trying to solve, because we still have algebra in also in geometry. So if you have a line segment where you're trying to solve for x, and say for instance one line segment is 2x plus 5 and it's congruent to 5x plus 2, and it asks you to solve for x, all you're saying is 2x plus 5 is going to equal 5x plus 2 and solve for it. Any questions on congruency? Now, midpoint, we basically touched on it already, but that is during the segment addition section. So midpoint of a line segment or a line is the point that separates the line into two congruent or equal parts. So if I have line A and line B, and I have a point M. Point M tells me that it's the midpoint, and not only is the midpoint, that this side equals this side. Now, to get the midpoint, there are several things that you must keep in mind. One thing is, if there is a midpoint, that means AM or ray AM equals ray MB. Also, ray MB is half of line AB. So of course, if AB is 14, Half of 14 is going to be 7. Therefore, MB is half of AB. Vice versa, line AB is 2 times rate MB. What that simply means is that in order to get the measurement of AB, I need to multiply 2 times the measurement of MB. So either way you split it, know that when you're trying to find the measurement of the other side of the line or try to find the measurement of the line as a whole, you can find that information based on what you're given. So say for instance, I am told that M is the midpoint of line AB and the measurement of MB is 7. What is the total measurement of line AB? Well, if we know that MB is 7, and we know that the total measurement of the line would be 2 times the 2 times of MB, then all I would do is take 2, multiply it to 7, and say that the line AB equals 14. Same thing if I have the total measurement of line AB, which is 14, and I want to know the measurement of AM or the measurement of MB, and M is noted as the midpoint. I simply take my 14, I divide it in half, and I say that MB equals 7. And since MB is 7 and it's the midpoint, that means AM as well is 7. Any questions? All right, moving along, we have postulate 4. Postulate 4 is about intersection. It says if 2 lines intersect, they intersect at a point. That's it. Postulate 4 simply says that if 2 lines cross each other, they meet at exactly 1 point. Now, as we mentioned earlier, if you have 2 lines and they're never touching, those are still parallel lines. So that means these 2 lines never touch. That means they won't have any points in common. Intersection and perpendicular lines, they meet at 1 point. Parallel lines, they meet at no points. Now, postulate 5 says that through 3 non-collinear points, meaning I have a point here, and a point here, or your point can be anywhere, but it has to be non-collinear, meaning that they do not all connect on the same line. If it is non-collinear, it simply means they have the same plane, or they exactly have one plane. So you have 3 points, they're non-collinear, meaning they're not all on the same line. They have the exactly one plane. So through 3 non-collinear points, there is exactly one plane. Now, postulate 6 says if 2 distinct planes intersect, then their intersection is a line. So I'm going to draw this to the best of my abilities, or I probably can find a picture of a non-collinear plane. That's what I'm looking for. This. Perfect. So if you look at this box, you should be able to see the 2 planes here, here, and here. So where they meet, which is right here, that is called a straight line. So postulate 6, if 2 distinct lines intersect, then their intersection is a line. So if I extended those 2 boxes out, those are 2 planes that when connected or intersected of each other, they make a distinctive line. Pretty neat, huh? Now, postulate 7 says if I have two distinctive points, given two distinctive points in a plane, the line containing these points also lies in the plane. So not only do you have 2 points on the plane, you also have a line on the plane. Because of course, if it's collinear and the collinear points are on a plane, that means the line's on that plane as well. So you either have a plane going from left to right, or you have a plane that's going up and down, but it is exactly one plane. So if it's on exactly one plane, that means it's on exactly one line. Last but certainly not least, we have a theorem listed, which I want you to distinctively remember. Theorem, because we're in chapter 3 of our geometry book, which again, thank you so much to my sister Angel for donating these books to me. Theorem 3.31. You're going to see a lot of theorems. You're going to see a lot of postulates. You need these theorems and postulates in order for you to do your proofs. Theorem 3.3.1. The midpoint of a line segment is unique, meaning that is the only point that separates that line segment. That is what makes it unique. Nothing else can separate or split the line segment into two congruent lines than a midpoint. Any questions before we move on? Next, we have postulate 8, which of course we've already touched on and discussed, but nonetheless, postulate 8 is a protractor postulate, which simply means the measure of an angle is a unique positive number. The measurement of an angle is a unique positive number. Simply means it can never be negative. Now, postulate 9 is angle addition postulate, meaning if I have a point that lies in the interior or the inside of an angle, then the measurement of the two angles should equal the total angle. So let's say this is D, this is A, B, and C. Well, the measurement of angle A, B, D plus the measurement of angle D, B, C, it equals the measurement of A, B, and C. So postulate 9 simply is angle addition postulate, and it simply means if I have a point on the inside of the angle and I draw a line through it or draw a ray through it, because the start point is B and it goes into the direction of D, then it splits it into two angles, and those two angles measured together give you your total of the original angle, or the measurement of the original angle. Now, of course, earlier I gave you the acute, the right, obtuse, and straight angle. But we do have one more angle. This is called the reflex angle. The reflex angle simply is the angles that are greater than 180 degrees. So, what does that typically look like? Well, you may have an angle like this, or an angle like this. But what makes it distinct and makes it reflexive is the circle or opening that's drawn around it. And typically when it's drawn like that, that means it is greater than 180 degrees. And of course, the arc is necessary for this degree measurement because it indicates and lets us know that it is greater than 180 degrees. So you can have a measurement of 337, or you can have a measurement of 225. Whichever your degree measurement measures, know that if you see a big circle like that, that means we have a reflex angle, and a reflex angle will be greater than 180 degrees. Now, of course, it stops being an angle angle measurement when you get to 360 degrees. Because, of course, 360 makes a circle. Any questions on my reflex angle? Moving right along, we have classifying pairs of angles. So what you will see are different definitions of angles. So first thing we have are two angles are adjacent if they have a common vertex and a common side between them. So remember, when we just did the segment addition. Well, this is also considered adjacent angles. So, two angles that are adjacent, they have a common vertex and a common side. So, since BD is between A and C, that means angle ABD is adjacent to angle DBC because they have the same shared side of BD. And a vertex or point of B. Now, adjacent angles aren't always like this. Some of them will look like two right angles going into two different opposite directions, but they share the same side. So they are considered adjacent to each other because they share the same side in the middle. Next, of course, we have congruent angles. Congruent angles simply means they equal each other. And of course, they typically denote the angle measurement with 1, 2, maybe 3 lines, depending on the angles. But a measurement of angle 1 being congruent of angle 2, it can be proved because the definition of congruent angles is that they have the same measure. So congruent angles are two angles with the same measure. So if they measure the same, they are congruent to each other. Next, we have by definition the bisector. The bisector is just like the two angles that are considered adjacent to each other. Also, it brings back to our memory of the postulate of angle addition. So what that simply means is I have angle A, B, C. Angle ABC is bisected or split in half by ray BD. Therefore, the angles are of the same measure. So bisector of an angle is the ray that separates the given angles into two congruent angles. So ray BD, when it bisects ABC, it causes angle ABD and DBC to have the exact same measurement. So if ABD is 15, based by definition, intersecting, that means angle DBC is 15. So when we're dealing with our definitions, know that bisecting ABD and DBC, that my angle measurements are the same. Now, another definition we will be working with is complementary angles. Complementary angles simply means these angles together add up to 90 degrees. So, a ray splits my right angle into two measurements, or it'll bisect into two measurements. Either measurements are going to be the same or they're going to be different. But angle ABD plus angle DBC, when they're added together, they must equal 90 degrees in order for them to be complementary. Now, remember I mentioned complementary in the beginning. So complementary simply means the sum of two angles that equals 90 degrees, which also means each angle complements each other. Then, of course, you have complementary, and then you have supplementary. Supplementary is the sum of 180 degrees. So you have a straight line. That straight line can be split into two angles because it has either been intersected by a ray or it has been bisected by a ray. But those angles must measure together, added together, because they're supplements of each other. When added together, they should equal 180 degrees. So if my angle measurement here is 70, that means my other angle measurement must be 110 for it to be supplementary, because 110 plus 70, 180. Now remember these definitions because you're going to need them when we start doing what? Proofs. Now, another definition we are going to look at are vertical angles. So you'll have two lines that are intersecting with each other. Now their measurement will be congruent if and only if they have vertical angles. Simply means that they are congruent because of the point in the middle. So line A, B, C, and line F, B, D are congruent to each other, or angle DBC is congruent to angle ABF because they have vertical angles. Same thing for angles ABD and FBC. They're congruent based on the fact that they have a common vertex. And if they have a common vertex, that means they have two vertical angles. Now, if you notice, you have two straight lines, and each straight line, of course, gives you supplements or supplementary. So, by definition, you have supplementary angles with two vertical angles, and you would also have two vertical angles on either side. So if based on the fact that B is the vertex and the measurement that's going around, or the opposite area, if this is 10, then this is 10. So if this is 10 and this is 10, that means the other two must be 170 in order for it to, one, be supplementary, and two, have the same measurement of angle. Any questions on vertical angles? All right. Theorem 3.41. Which you should know, but is repeated so you know that it is a theorem. Theorem 3.4.1 simply says there is one and only one bisector in a given angle. So if you have an angle and it's bisected by a ray, it can only be bisected by one ray. You won't see multiple rays bisecting an angle. Now you may see angles that have multiple rays coming out of them, but it won't be a bisector. So theorem 3.4.1, there is one and only one bisector for a given angle. So if it has one and it says it bisects, it is a bisector. If it has more than one, not a bisector. And of course, by definition, if it says it's a bisector, it is a bisector. You can't assume that it's bisecting. You have to, by definition, it becomes bisecting when you see that the angle measurement are the same. So you can only bisect an angle once, and to know that it's bisecting, the measurement of both angles will be the same. Now, the reason why I gave you guys these proofs and postulates, theorems and postulates, because we are going to be introduced to proofs. Proof is simply saying, hey, 2x plus 5 equals 4. How can I prove it? Now, remember, we had the strategy of Pauli's 4-step strategy. This is where this comes in handy, because we are going to work on doing our proofs, proving different answers. So now you are going to have different properties, different theorems, and postulates. And based on these postulates, properties, and theorems, you can prove your case of your answer. So we have the addition property of equality, because we're going to deal with the properties of equality, and we are going to deal with different other properties that allows us to do our proofs. So first proof of equality is the addition property. That means A will equal B if and only if A will equal B if and only if A plus B, A plus C equals B plus C. So addition property says that if A plus C equals B plus C, then A equals B. Same goes for subtraction of inequality. If A is minusing C and B is minusing C, therefore A equals B. If A is being multiplied by C and B is being multiplied by C, then A equals B. If A is divided by C and B is divided by C, where C does not equal 0, because of course if C equals 0, the answer is undefined. So if A is divided by C and B is divided by C, A equals B. So the addition, subtraction, multiplication, and division property of equality simply says these two can equal because of this property. Next, we have our reflex property. Reflex property simply means that A equals itself by definition. Symmetric property says if A equals B, then B equals A. Looks more like the commutative property, right? For when A plus B equals B plus A. Same concept. Here we go again with the distributive property. If A is being multiplied to B and C, then it's A times B and A times C. Distributive property. I'm multiplying the outside to everything on the inside. Substitution says, well, if A equals B, then I can replace A with B in any equation. And of course, we have the transitive property that if A equals C and B equals C, then correction, fix that. If A equals B and B equals C, that means A equals C. If A equals B and B equals C, then A equals C. Transitive property. So, when doing proofs with these type of properties, typically you are solving for X, solving for Y, solving for B, solving for C. So now, based on these properties, we can do a proof. So say you are given 2x minus 3 equals 7. The proof is that you must find x equals 5. So with proofs, you are given the beginning, you are giving, and you are given the end. You have to prove the in between. You are given the problem and the answer, but you have to solve or show how you found that answer. That is what proofs are. So, first things first, you always give the given. The given is always 2x minus 3 equals 7. The first proof is given. Now you start solving your answer. So, to get 2x by itself, you know that is solving for x. So to get it by itself, I'm going to add 3 on both sides. Adding 3 on both sides in a proof is called addition property. Remember earlier we said if A equals B, then that means A plus C equals B. So what you do on one side, you do on the other side, right? So the first one is given. The second one in the proof is addition property of equality. Then you have 2x equals 10, and that is considered substitution. Why? Because if A equals B, then A can replace in any equation. So if we add 3 on both sides, substitution simply means we are combining like terms. Once we combine those like terms, then we continue on by solving for our x. So now the next step, of course, is division of equality. Because in order to get this 2 by the x by itself, I must divide by 2, right? So the next step in the proof is called division property of equality, because I'm dividing 2 on both sides. Then once I have divided 2 on both sides, my x becomes 5 based on substitution. So in geometry, proofs when it comes to solving for x is simply taking each step of the letter that you're solving for, or the variable that you're solving for, and giving a property to each, or reason to each of those properties. So proof given, you have 2x minus 3 equals 7. The proof is that x will equal 5. You have to show me based on properties how 2x minus 3 equals 7 is going to turn out to be x equals 5. So if you're solving 2x minus 3 equals 7 and your answer end up being x equals 5, how you find it are the reasons of the proof. Any questions on this part of the proof? Now you're going to have strategies of proofs. First strategy is the first line of proof. General rule, the first statement of the proof includes the given information. Also, the first reason is given. So, anytime you are starting a proof, the first thing you always do is the given. Strategy number 2 is the last statement of the proof. The final statement of the proof is the proof statement. And you don't say proof, you state how did you prove that statement. Next, we have 2 additional properties, but these properties are properties of inequality. So, addition property of inequality, if A is greater than B, then A plus C is greater than B plus C, and vice versa. If A is less than B, then A plus B is less than A plus B. If A plus C is less than B plus C. Of course, for every addition is its component of subtraction, which simply means if A is greater than B, then A minus C is going to be greater than B minus C. And still applies to the vice versa, which is if A is less than C, if A is less than B, then A minus C is less than B minus C. Now, typically when you see something like this, you'll see something such as given when you're dealing with proofs. your given would be MN is greater than PQ. And typically it would look like this. And you have M, N, P, and Q. So your given is M, N is greater than PQ. You have to prove that MP is greater than NQ. So now, first thing we must do is give the given, which is MN is greater than PQ. That is our given. That's the first part of our proof. That is given. So now, if MN is greater than PQ, if you remember our addition property inequality, number 2 says that if MN is greater than PQ, we can prove that by saying MN plus NP is greater than NP plus PQ. And that is considered the addition property of an inequality. So now we have established the addition property of inequality. We now can say that MN plus NP equals MP. Also, we can say NP plus PQ is NQ based on segment addition postulate, which is what we had earlier. The segment addition postulate says that if MN is added to NP, or if A plus B, well, AM plus MB, which is what we had earlier. AM plus MB, that equals AB, right? So then NM plus NP, that gives me my MP, and NP plus PQ, that gives me my NQ. So once we define those based off of segment addition postulate, all we have to do now is substitute MN plus NP for MP and MP plus PQ for NQ to prove that If MN is greater than PQ, then we proved that MP is greater than NQ. We gave a given, we gave a property, we gave a postulate, and we proved through substitution. Any questions? Now, moving right along in proofs and proving certain proofs, we have vertical lines and horizontal lines. Vertical lines mean it goes up and down. Horizontal means it goes left and right. Now, a perpendicular line, of course, makes four right angles. But simply put, when a vertical line bisects a horizontal line, or a horizontal line bisects a vertical line, they are perpendicular and they have congruent adjacent angles. So theorem 3.6.1 is if two lines are perpendicular, then they meet to form right angles. So, what would that look like as a proof? Let's say you are given that line AB line AB is perpendicular to line CD, intersecting at point E, prove that angle AEC is a right angle. So, first thing, of course, we do is we give the given that AB line AB is perpendicular to CD and it's intersecting E. That is the given. And typically when you're writing something particular symbol, Of course, 1 is always the given. 2, if AB is perpendicular to CD, then AEC is congruent angle AEC is congruent to angle CEB, and that is based off of when perpendiculars meet to form congruent adjacent angles. That is definition. So definition says perpendiculars are two lines that meet to form congruent adjacent lines. Now remember, I said remember definitions, remember the postulates and the theorems because you need them for your proofs. This is what I mean when I said need them for the proofs. So now number 2 says that the measurement of angle AEC is congruent to the measurement of angle, make sure I put in measurement of angle AEC is congruent to measurement angle CEB by definition of perpendicular lines that form. Then, of course, you have number 3, which is by definition well, correction. This is, fix this. I mixed up my lines. I do apologize. Number 3, by definition, if my angles are congruent of each other, that means the measurement of those angles are equal to each other. Next, in my proof, probably would help if I maximize this even better. So next in my proof, measurement angle AEB is a straight angle. And the measurement of that straight angle is 180 degrees. So we established that based off of the measurement of a straight angle equals 180 degrees. Stay with me because we are still continuing and we are going somewhere with this, okay? So we have defined and given the measurement of 180-degree angles. And in those 180-degree angles, we say that, hey, well, if we define that the measurement of angle AEB is a straight angle, then that means the measurement of angle AEC plus angle CEB equals angle AEB based on the angle measurement, angle addition postulate. So remember, if two angles added to each other, they are part of the angle addition postulate. Also, you could say here that angle AEC plus the measurement of angle CEB, that equals the measurement of angle AEB because they're supplementary angles. So you can say it's angle addition postulate or based on the definition of supplementary angles. And so based on the supplementary angles, we know that, hey, that equals 180 degrees. So now, 180 degrees. So now, number 6 in the proof says that measurement angle A measurement angle AEC, because remember, we're still dealing with the measurement of these angles. So measurement angle AEC plus the measurement of angle CEB, it equals 180 degrees based on substitution. Then if AEC plus CEB, which what we had earlier of number 2, if measurement angle AEC plus the measurement of angle CEB equals 180 degrees, then based on substitution again, I can say that the measurement of angle AEC plus itself equals 180 degrees, or you can simply put 2 times the measurement of angle AEC equals 180 degrees. Then once you have established that based off of substitution, we can say that the measurement of angle AEC is 90 degrees based on the division property of equality, which means I took my 2 and I divided it on both sides. So I divided 2 on the left side and divided 2 by 180, and that gave me 90 degrees, which allows me to prove that the angle AEC is a right angle because if the measure of an angle is 90 degrees, then it is a right angle or the right angle definition. Any questions on proving my theorems? All right, guys, that's it on proofs. Well, that part of proofs. Now, we have been talking a lot about intersecting and perpendicular lines. What I want to now focus on are the parallel lines. Parallel lines can be formed based on a line, two lines, a line and a plane, or two planes. And typically, when you have two lines that never touch, a perpendicular line can be formed within those two parallel lines. So, postulate 10. Postulate 10 says through a point not on a line, exactly one line is parallel to the given line. So when a point is not on a line, like the point's out here, then exactly one line is parallel to the given line, which means it's out here. And typically, when you have parallel lines, they are either going to have perpendicular or a bisecting line, like so. Now, if it's not perpendicular, then what you have is a transversal. And a transversal is a line that intersects two or more other lines at a distinct point, at distinct points, and they all line on the same plane. Now, when a transversal cuts through two or more lines, you form interior angles and exterior angles. So you have angle 1, 2, 3, 4, 5, 6, 7, 8. So now, interior angles are, of course, the angles on the inside. So angles 2, 3, 6, and 7, those are considered interior angles. They are on the inside. Whereas 1, 5, 4, and 8, those are the exterior angles. Those are the angles that are outside. Now, typically, we deal with these type of angles based on congruency. So, corresponding angles are congruent to each other. Well, wait a minute. Yes, corresponding angles are typically congruent of each other. So, if a corresponding angle is listed like this. If angle 1, if I'm looking for the corresponding angle of angle 1, the corresponding angle of angle 1 would be 3 because they're on the same side and they're congruent of each other. Same thing would be for corresponding angles of 2 and 4. They're on the same side and they're equal to each other. Same thing for 5 and 7 and 6 and 8. Those are corresponding angles and they're congruent to each other because they are corresponding angles. Now, alternate interior angles says that, hey, this angle equals this angle based off of alternative interior angles. Just like you have vertical angles, which are alternate of each other. So 1 and 6 are vertical, 2 and 5 are vertical, 3 and 8 are vertical, and 7 and 4 are vertical. So based on that, the alternate interior angles would be 3 and 6. Because if you notice, alternate means they're on opposite sides, but they still have the same measurement. So opposite side, same measurement on the inside. So 3 and 6, those are interior angles. 2 and 7, those are alternate interior angles. Now, alternate exterior angles mean that they, of course, are outside. But not only are they outside, but they're alternates of each other. So 1 and 8, those are alternate exterior angles, meaning they equal each other. They're congruent of each other. So when you find the congruency of an alternative exterior angle, well, the alternative exterior angle of 1 will always be 8. And the same thing for 4 will always be 5. Because based on that angle definition of them being congruent, alternate exterior angles equal each other. The angles were. I guess Siri thought I was talking to her. Sorry about that. So postulate 11 simply means if 2 parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent. If 2 parallel lines are cut by a transversal, then the pairs of alternative angles are congruent. That's theorem 4.1. And the same for 4.12 and 4.13. 4.13 says if 2 parallel lines are cut by a transversal, then alternate exterior angles are congruent. So everything that you see is based off of congruency. Vertical, corresponding, and alternate angles, they are based off congruency. Now, you also can prove in substitutions based on the fact that some angles are considered supplementary. So the theorem of 4.14, it states that if two parallel lines are cut by a transversal, then the pairs of interior angles on the same side are of the transversal are supplementary. So that means 2 and 3 are supplementary of each other, and 6 and 7 are supplementary of each other. Based on the theorem that if two parallel lines are cut by the transversal line, then the pairs of interior angles that are on the same side, like 2 and 3 and 6 and 7, they are considered supplementary of each other. Any questions on the parallel postulate or special angles? All right, moving on to our next section. Are you guys enjoying what we're doing so far? Do you have any questions of what you have just learned so far? Any questions? Well, guys, it looks like based on my book, I have already covered a lot of this stuff. And convex polygons. A polygon is a closed plane figure whose sides are line segments that intersect only at the endpoints. So, of course, you have different types of polygons. And based on its prefix, it lets you know what it is. So, triangle, tri is 3. So simply, a triangle is a 3-sided and 3-angled polygon. Quadrilateral, which is a square, rhombus, trapezoid, all that good stuff. Quadrilateral means that it's 4 sides. 4 sides, 4 angles. Penta, and please excuse it in advance. Pentagon. Pentagon, penta, 5. 5 sides, 5 angles. Hexagon. Hexagon, of course, means it has 6 sides and 6 angles. So 1, 2, 3, 4, 5, 6. And so you also have a heptagon that's 7, octagon that's 8, nano or nanogon that's 9, and decagon that's 10. So whenever you see those type that have different size, know that they all have their own name. Depending on how many sides is the type of polygon that it is. Any questions on the polygons that we've mentioned? Now, we are going to talk about symmetry, line of symmetry, axis, and point of symmetry. So all of symmetry, transformations, slides, translations, reflections, and rotations. And rotations based off of angle rotation and center rotation. What does all of that mean, and what does that all look like? So, say for instance, we have a rectangle and a line drawn in the middle of that rectangle cuts it in half. Line of symmetry means I should be able to take my shape that I've drawn and fold it over each other to make a perfect symmetric fold. So symmetry is basically saying that the left side equals the right side, split by a line. And the line, of course, can go either vertically or the line can go horizontally. But know that you have at least one line of symmetry if both equal each other. Now, point of symmetry is exactly that, a point. Typically, it may be in the middle. And what it'll do is give you the direction of your symmetrical point. And it could be drawn from left to right, up and down, or if you had dealing with rectangles, it could be drawn diagonally. And if it's drawn diagonally, that's still considered a symmetry draw. So a figure has a symmetry with respect to a point if for every point that is on the top of the line, there is a second point at the bottom of the line, and then the point in the middle forms a midpoint. So you know you have a point of symmetry when the point in the middle of your polygon is a midpoint by definition. Now, at any given moment, you will have symmetry and you will have different things going on a graph. Typically, if you have a triangle, and you draw another triangle, there are different things that can happen with that triangle. First thing you would notice is that some triangles have what we call our translation or slides, meaning that the triangle can be moved in different directions. I can either go 2 units to the left, 2 units to the right, 4 units to the left, or I can go 2 units down and 4 units to the left, to the right. So translation simply means I'm sliding from left to right and up and down. Then, of course, you have after translation is reflection. Reflection means you remember how we were talking about symmetry and how you could fold those two in half? Well, reflection is basically of the same concept, meaning I am reflecting on either the x-axis, the y-axis, or its origin, or on the given line. So say, for instance, if I have triangle A, B, C, and triangle close enough, triangle D, E, F. To know that they are reflections of each other, the points must flip in the same pattern, but be in the same side. So A would be to A, C would be to D, and B would be to E in order to prove the reflection. Most importantly, your reflection will give congruency. So anytime you're dealing with reflection, you're dealing with basically congruency. Now, rotation. Rotation simply means I am going to rotate or revolve Let's see if I can get it to do what I want it to do. There we go. So whenever you are dealing with rotation, you simply are rotating at a certain degree. So either you rotate it, if you started here at M and you get to X, the rotation gives off a degree measurement. here. Do it that way. It gives off a degree measurement, and you're able to say, okay, this is rotated based off of a 45-degree clockwise motion or a 45-degree counterclockwise. So either it's going to the left or going back counterclockwise, or it's going forward and to the right clockwise. And if it is, you're able to measure it and say, hey, this square was rotated. The second square rotated is a rotation of the original square by 45 degrees. Any questions on the rotations, reflections, all of that good stuff? Now, I must give you some definitions, and I must give you a few theorems and postulates for proving purposes. So, definition, two triangles are congruent if the 6 parts of the first triangle are congruent to the 6 corresponding parts of the second triangle. What they mean by 6 parts, they mean the 3 sides and 3 angles. So triangle ABC and triangle DEF can be congruent if all 6 parts are proven to be congruent. Meaning angle A equals angle D, side AC equals DF, or angle C equals angle F. By definition, two triangles are congruent if the 6 parts, which is the 3 sides or the 3 angles, are equal to each other. So you'll have reflexive property of congruency, you'll have symmetric property of congruency, and you'll have transitive property of congruency. So simply meaning if you have triangle ABC, then triangle ABC equals itself, reflexive. If triangle ABC is equal to triangle DEF, then triangle DEF is equal to triangle ABD based on symmetric property. Or if A equals B, then B equals A. Symmetric property. Also, if triangle A BC is equal to triangle DEF and triangle DEF equals triangle GHI, then that means triangle ABC equals triangle GHI based on the transitive property. So these are the three properties you will see and deal with when it comes to congruency of a triangle. So to prove that they are equal to each other, we have a few postulates. So postulate 12 is based off of the side postulate, which says if three sides of one triangle are congruent to three sides of a second triangle, then the triangles are congruent based on side postulate. So, say for instance, you are given triangle AMC and triangle DMB. You are given that A and C, AB and CD are bisected by M, and that AC is congruent to DB. So that means these sides are equal to each other. So now, if AB is bisecting by CD, well, based on definition, that means if they're being bisected by M, that means AB, AM is congruent to MB, and CM is congruent to MD. Therefore, based on postulate side, if AC is given that it is congruent to DB, and that M is the midpoint which bisects A to B and C to D, then that means A to M is congruent to M to B, and C to M is congruent to M to D. So if all of those are congruent of each other, that means triangle AMC is congruent to DMB by proving the postulate of side. And that's usually denoted as SSS. So now, My next postulate is based off of side angle side, which states if two sides and the included angle of one triangle are congruent to two sides and the included angle of a second angle, then the triangles are congruent based off side angle side. So now, say for instance, triangle A, B, C, triangle D, E, F. If the given is measure side A, B is congruent to DE, angle B is congruent to angle E, and side BC is congruent to side EF, then the postulate of side angle side is proven by definition because you have the same side congruency, the same angle congruency, and the same second side congruency. So if all three check, that gives you just side angle side. Now remember, side angle side is making sure that the angle is in between those two sides. If the angle is not in between the two sides, it's not side angle side. In order for it to be side angle side, the angle, of course, must be in the middle. Next postulate is postulate 14. And in postulate 14, we find that if you have two angles and the included side of one triangle, and two angles and the included side of a second triangle, then the angles are congruent based on the postulate angle side angle. So, say for instance, back to A, B, C, and D, E, F. If you have an angle B and it is congruent to angle E, you have side BC is congruent to EF. And then if you have angle C is congruent to F, angle F, then you have proven your postulate based on, you have proven that the triangles are congruent based on the postulate of angle side angle. And if you notice, angle side angle postulate, you have an angle on both sides with a side in the middle. So if the side is not in the middle or corresponding between the two angles, it is not considered angle side angle. Now, there is a theorem that we must discuss, which is angle, side. The other three are postulates. The theorem is angle, side. If you can prove the theorem, of course, remains true. What does that mean? What does that look like? Well, the theorem of angle, side. All that means is if I have two corresponding angles and a side, two corresponding angles and a side, I can prove my theorem of triangle congruency by saying the theorem angle, side, which is if two angles and a non-included side of one triangle are congruent to two angles and a non-concluded side of the second triangle, then they are congruent based on angle, side. So given that angle A is congruent to angle D, and angle C is congruent to angle F, and side BC is congruent to side EF, we prove that based off of given definitions that angle or triangle ABC is congruent to triangle DEF based off of angle, side theorem. All right, moving on. We have a definition which is corresponding parts of congruent triangles are congruent. So, say for instance, you have a ray that bisects triangle TWV and the ray WZ bisects this triangle, we can prove that TZ is congruent to VZ. So if I'm given that WZ is bisecting triangle TW is bisecting angle is bisecting TWV, angle TWV. Also, I am given that side WT is congruent to side WV. So, if WZ bisects TWV, we can prove that TZ and ZV are congruent based on CPCTZ, which is corresponding parts of congruent triangles are congruent. You can put CP, CTC. That is the abbreviation of corresponding parts of congruent triangles are congruent. Now you can prove this based on this strategy. In a proof, two triangles must be proven congruent before corresponding parts of congruent triangles are proven. So, for this example, we are given the givens, which are WZ bisects TWV, which is that angle. And we also have angle TWZ is congruent to VWZ. So TWZ, VWZ. Based on the definition of an angle that is separated into two congruent angles, TWZ is congruent to VWZ. So that is given. That is given, and then by definition, that is also given. Also, WZ is congruent to WZ based on what? Identity, right? Not only identity, but reflexive property. That's saying that if that A equals A, B equals B, so therefore ray WZ can equal ray WZ based on reflexive property. So I'm given that WT is congruent to WV. I find out based on the bisecting of angle TWV by WZ that because it was bisected, that angle TWZ and VWC, those are congruent angles. Because by definition, if you bisect something, that means they have the same equal angle measure. Then, of course, reflexive property says WZ is equal to itself. So we prove that the triangle TWZ is congruent to triangle VWZ based on the postulate side angle side. So if we prove that corresponding parts of congruent triangles are congruent, well, once we prove that these triangles are congruent, we can then say TZ is congruent to VZ based on congruent parts of congruent triangles are congruent. Any questions on proving the congruency of these triangles based on CP-CTC? All right. Next, we have the proving of right triangles being congruent to each other based on the hypotenuse leg theorem. which simply says if the hypotenuse are congruent and a side is congruent, then corresponding parts of congruent triangles are congruent. So say we have A, B, and C, or correction, A, B, and D. Fix these right quick. Corresponding with my triangles correctly. So, say for instance, your triangle ABC and your triangle ABD has to be proven that they're congruent and that side CB is congruent to side DB. Now you are given that AC is congruent to AD. You also are given that AB is perpendicular to CD. So that means you have right angles by definition. So first given is AB is perpendicular to CD. So if AB is perpendicular to C and D, by definition, angle 1, angle 2 are right angles based on the definition of perpendiculars. Then you have side AC is congruent to AD based on identity or reflexive. AB is congruent to AB based on identity. AB is congruent based on AB based off identity. AC and AD are congruent based on that it was given. Therefore, triangle ABC is congruent to triangle ABD based off of the theorem hypotenuse leg, because the hypotenuse is always opposite of the right angle, which would be here. And then we have a leg that they both share, which is AB of both triangles. Therefore, triangle ABC is congruent to triangle ABD based on hypotenuse leg. And because we have proven the congruency of the triangles, then CB is congruent to BD based off of C, P, C, T, C. Any questions on CPTC or hypotenuse leg? All right, moving on to Pythagorean theorem. Pythagorean theorem is typically based off of the square of the length of C, which is the hypotenuse of a right triangle. It equals the sum of the squares of the lengths AB of the legs of the right triangle. So C squared equals A squared plus B squared. Or so A, B, C. So Pythagorean theorem is the squaring of the hypotenuse, and the squaring of the hypotenuse is the sum of the squares of the legs. And you can find each leg or the hypotenuse based on the square root property. So you're going to have 3 different square root properties when dealing with Pythagorean theorem. So if C squared equals A squared plus B squared, in order to find the hypotenuse, I would then have to take the square root on both sides, which would leave me with C, because the square root of a square is itself A squared plus B squared. Now, if you are trying to find one of the legs, you got C squared and it equals A squared plus B squared. And say, for instance, you're trying to find, you have the hypotenuse and you have one of the legs and you want to find the other leg. All you would do is, say we're looking for leg B. You subtract A squared on both sides, which gives me C squared minus A squared equals B squared. And then I would take the square root of B squared. And since I'm taking the square root of B squared, I must then take the square root of the difference of C squared and A squared, which will give me of my legs. So square root of C squared minus A squared will equal B, or the square root of C squared minus B squared will give me A, all depending on which leg you're looking for. So when you're dealing with this, you're dealing with these square root properties. All right, moving on. Have a few more sections that I'm going to touch bases on with you guys, and then we will be done. I hope that what I've given you have been of great assistance, and that you understand what we are doing. Next, we have special right triangles. Special right triangles have a specific definition when it comes to solving based on Pythagorean theorem or based on the measurement of those sides. So, say for instance, I have a right triangle. And the right triangle has two 45-degree angles, which means more than likely it's an isosceles triangle. Because if the angles, you have two angles that are equal, that means you have two sides that are equal with the hypotenuse. So, if those two are equal to each other, then based on how we find our answer for our hypotenuse, which becomes a square root of 2, we find that by solving the Pythagorean theorem. So we know that c squared equals a squared plus b squared. Well, if two of the sides are the same, then it's c squared equals a squared plus a squared. Of a squared plus a squared gives me 2a squared, because 1a squared plus another a squared, now you have 2a squares. Then we take the square root on both sides, which allows my c to just be c, because square root of c squared, the squares cancel, which leaves me with c. And then you have the square root of 2a squared. Now, how with a with the square root of 2? Well, if you remember, a number and a letter, or number and a variable, is simply a number times a variable. So whenever you have a number and a variable multiplying to each other, you can separate them under two different square roots. So if a variable is multiplied to a number under a square root, you can separate that number from that variable and make two square roots. So then once I separate the two, c equals, well, the square root of a squared, the squares cancel, so that leaves me with a, and then you have the square root of 2. Now, we won't go ahead and divide square root of 2 out, because square root of 2 is irrational, meaning it does not repeat and it does not stop. So when we're dealing with 45, 90-degree angle, to find the hypotenuse, if we have one of the legs, all we would do is make it a square root of 2. So if a is 5, then The hypotenuse is 5 square root of 2. Now, what if we have our triangle still, and we know that it's a 45, 45, 90, but I have my hypotenuse. Also, my hypotenuse doesn't have a square root of 2. It's a whole number. How do I find that answer? Well, we know that in order to find the length of the hypotenuse, that means you have the length of this side and this side to find. So, how do I find that side? Well, if A is the square root of 2, well, if the hypotenuse by definition is the square root of 2, then we can easily say 6 equals A square root of 2, because that is the definition. We then can divide both sides by the square root of 2. To get my A. So 6 over the square root of 2, that equals A. So whenever you have a square root in the bottom of a denominator, you must get rid of that square root, because a radical cannot be a denominator. Just like 0 is undefined in the denominator cannot be a square root. So to remove the square root, or to get rid of the square root, we must multiply top to bottom square root of 2. And of course, if I multiply square root of 2 to square root of 2, that gives me 6 square root of 2, and that is over 2. And of course, 6 divided by 2, because those two numbers can be divided into each other, will leave me with 3 square root of 2. So that means A equals 3 square roots of 2. So whenever you're solving a 45, 45, 90, your hypotenuse is whole, set by definition for them to equal each other. And once you do that, you can have your both of your sides. Now, where there's a 45, 45, there's also a 60, 30. Because, of course, all of this must equal to 180. And if you have an angle of 90 degrees, this special right triangle states that a 30, 60, 90 theorem in a right triangle, the hypotenuse has a length that equals twice the length of the shorter leg and is the square root of 3 of the longer leg. So you have the longer leg, you have the hypotenuse, which is A. The hypotenuse is 2 times of A. And let me switch those around right quick. And if you notice, the shorter angle the shorter leg corresponds with the smallest angle, and the longer leg corresponds with the biggest angle. So now how did they come up with this? Well, you have C squared equals A squared plus B squared. Now, A is, of course, the bigger leg. It's the shorter leg. Well, A squared is the shorter leg, therefore it will remain as A squared. Then, of course, you have C squared. We know that C squared, by definition, if you already have A squared, then the hypotenuse is 2 times of A. So basically what they did was they took the hypotenuse definition and the shorter leg definition to find the longer leg definition. So once they did that, they said, hey, 2A squared gives me 4A squared equals A squared plus B squared. Then, of course, to get B squared by itself, they subtracted A squared on both sides, which, of course, when you subtract A squared on both sides, that gives me 3A squared equals B squared. And, of course, you take the square root on both sides. And 3A, the square root of 3A squared equals B, or B equals the square root of 3A squared. We know by definition they're multiplied to each other, so I can split them apart, where B equals the square root of 3 times the square root of A squared. And of course, B equals A square root of 3. And all you have to do in order to find your lengths is equal them to their definitions. And let me fix this right quick. Go back up this way. So I'm going to make sure that I write this correctly. So shorter leg, of course, is A. Hypotenuse is twice of A. And the longer leg is the square root of 3 of A. So with those two added together, they should give you your hypotenuse. Now, if you're looking for the longer leg and you have let's say you have the hypotenuse and you're looking for the longer and shorter leg. Well, go with 20. If I have 20 as my hypotenuse And I need to find my shorter and long leg. By definition, we know that the hypotenuse is twice of the shorter leg. So therefore, my shorter leg is going to be 10. Because if hypotenuse is 20, then half of the hypotenuse is going to be 10. So then if half of my hypotenuse is 10, then once I find that, I can easily say that my long leg is 10 square root of 3. And literally, you can find all of these things based on their definitions. Any questions on the special right triangles? Well, guys, that is it for geometry. I know that I unpacked a lot of information for you guys. So, of course, when this live ends, you can rewind, review, and it'll allow you to see what we went over. Of course, all the other videos from day 1 and day 2, those are listed on both my Facebook and my YouTube page. And of course, if you're in the Facebook, you can see it on my, you can see in the links that we have my Facebook and my YouTube page. What you have to do is, if you want to review based on YouTube, click on the link. You'll see geometry day 1, day 2, and this will be day 3 and our final day. And it'll allow you to review what we went over. Simply put, thank you for shaping up with me and wrapping this up with me. I'm so grateful that you guys were able to join me this morning, and I'm glad you were able to understand it. If you have any questions outside of this live and you are needing information on tutoring, better understanding of what you are being taught, if you need a deeper definition or a deeper breakdown of what was taught on screen, you can inbox me, you can DM me, you can IM me. You can also text me at 205-542-5062, 205-542-5062, or inbox me, IM me, and DM me on all of my social media platforms of Mathematics for You Tutorial Services, LLC. So there are no questions and nothing that needs to be answered or any additional information that you or guys are needing. I'm going to go ahead and end this live. And of course, Miss Chris has been looking forward to and enjoying this time with you. Now, if by chance that you are needing additional information, you know how to reach me. Also, next week we are going into Algebra 2. Algebra 2 is going to be a repetition of Algebra 1, but with some distinctive formulas, equations, and more expansion of what we learned from Algebra 1. So now, if you have any questions, of course, I'm always here to help you. I thank you for your time. I thank you for joining us. May you have a blessed and prosperous Friday. You have made it to the end of the week. I hope you enjoy it. We are off tomorrow, so you can rest for Saturday. You won't see me on Saturday. Get your rest because you earned it, because I gave you back-to-back days of nonstop geometry. And I know your brain is spinning like the clocks and clogs that are going spinning in my logo at the top. So if you have any questions, again, reach out to me. I am willing to help because guess what? All questions are important. And the question you have now, answer it as soon as possible. Other than that, this is Miss Chris of Mathematics for You Tutorial Services LLC, where we are changing mindsets one problem at a time. Have a blessed Friday. Enjoy your weekends. Be safe, and be sanitized because we are still in a pandemic, guys. And I'll talk to you later. Much love. Goodbye.